Welcome to Nature's CSI, Creepy Stories of Invasion. I'm Dr. Tom Stolgren. This is episode 6, Mapping and Modeling Invaders. Ecologists would be really happy if we could see everything out there in the world. We could easily map it and predict where it's going to go. But often we have a very small sample size. This is a 15% sample of my favorite painting, for example. Can you tell what painting it is? Well, it's Madame Monet and Her Son by Claude Monet. But having a small sample is typical in ecology. Sometimes we only see a small piece of the picture and we have to predict what the rest of the picture looks like. And that's our difficult task. For example, in 2007, we were given a small number of points of Asian carp. There they are in blue along the Mississippi River. And they asked us to determine where the carp may go. That's predicting where a species might be in space and time, and it's very difficult. And this was a preliminary model that showed, well, it could get to the Great Lakes, it could go up the Missouri, and it might even be found in the eastern United States someday. From those small number of points, we had to estimate where the Asian carp may be in the future. How do we do that? That's a good question, and I hope you packed a lunch. This is a little longer episode than some of the others. This is the information needs for mapping and modeling invaders. Well, you need information about the species themselves. What kind of a species are they? How do they move? How do they reproduce? Where do you think they're going to go? Then you need something about the environment, information about the temperature, precipitation, soils, and topography. You need to relate where the species is to those environmental characteristics. Then you have to evaluate the uncertainties of a spatial model. You may make guesses on where it is, but you might be wrong. You also have to look at future distributions in abundance. Where is it going to go? Because these things reproduce and move. And every time you do that, you have to evaluate the uncertainties of the temporal models. Really, what we're trying to do is institute an iterative process where you sample and model and sample again and expect surprises. It's really easy to find point dots, locations of species on a map. This is the New Zealand mud snail in California. Nice little dots show where the New Zealand mud snail is. Here's a map of Asian grass carp in the United States, again shown with dots. And we do this all over. We make global maps of pitcher disease, that terrible disease that's wiping out amphibians, again with dots. We might look at time series of dots, like in this case, the lionfish, locations from 1985 to 2011, and you see the red dots of the lionfish increasing over time. But dots only tell you so much, where something's located at the time it was sampled. It doesn't tell you about in between the dots, or where the dots are going to be next. And that's where modeling comes in. Predicting species in space and time is one of the toughest jobs ecologists might have. In this example, we have presence points, dots on a map, and we have an Excel spreadsheet or some data source that tells us exactly where they are, the latitude and longitude of those dots. But if we combine those dots with environmental layers of temperature, precipitation, slope, elevation, and many other predictors, we can run those through a model, a Maxent model, boosted regression tree, or random forest model, some kind of algorithm, and go from the dots to a probability, a predicted probability map. So this helps us estimate where the species may be from the dots that we have. We can also subsample those dots, move them into training and test data, and run several iterations so that we get a map of uncertainty when we're mapping and modeling. This is helpful. This is a map with error bars. It tells us where our model is convincingly accurate and where we have high uncertainty. Then we can go and verify the model with new data. We can sample in those areas of high uncertainty and repeat the process, the modeling process, so that your model improves over time. This is an example of one of our first models run with white pine blister rust, a disease that came from Asia. It settles in gooseberries and currants, and then moves it to 5-needle pines and pretty much wipes them out. So we had 918 presence points, and we quickly ran a model and found out, wow, we could really predict where this disease is hitting. And we can show, the data will show, and the models show how different it is from a random distribution. In this case, it follows that nice red and blue line is very different from random chance. In fact, we were 99% accurate in this first model. That's pretty high. We can also tell from the software what factors were the most important in predicting the distribution of this disease. And in this case, it was growing degree days, elevation, seasonality of precipitation, and also geology and humidity. That's where the bars are greatest, and those are the factors that had the most influence on the model. We can also look at individual response curves from those variables. In this case, we found out that if we had a large number of growing degree days, really warm areas, we had a low probability of the disease. And if we had a small number of growing degree days, like on the top of a mountain, we had a high probability of the disease. Elevation, it was somewhere in the middle. And in temperature seasonality, the probabilities were highest where the temperature seasonality was about moderate, the difference between summer and winter temperatures. This helps us define where the species can be found in other sites. We also looked at the number of plots that were greater than 90% affected by the disease, where white pine blister rust had come in and wiped out those 5-needle pines. And sadly, we found out that Glacier and Yellowstone National Park were being hit very heavily by the disease. It had not yet reached Colorado, but the maps and models suggested, hey, we better take a closer look at Rocky Mountain National Park in the near future because it looks highly susceptible to that same disease. Our next effort was looking at the habitat suitability of a freshwater diatom called Didymosphena geminata in the conterminous United States. It's a tiny little diatom, but when it gets in the stream, it turns it brown, like full of toilet paper. And the big fish disappear and the small fish stay behind. So fishermen really don't like this diatom exploding into their streams. And what we found out was different models gave you different results. So you have to be careful with modeling. You might want to test different models to find out what model worked best, which model was the highest accuracy prediction. In fact, models have all kinds of problems. So we have large caveat sections describing our results. Two models give you different answers, or a habitat specialist and a habitat generalist may give you different answers. You may have some areas of your habitat that are unsurveyed, and you can't help predict in those areas. You might have poorly surveyed habitats within the general area, and again, that might limit your predictions. You might have data from two time periods that are radically different, or different genotypes of a species that behave differently in responses to the environment. You might have different thresholds for your models, some mathematics I won't go into now, or you might be missing a big stream layer or some other environmental layer that's very important in the prediction. So we take some cautionary measures when we do our predictive models of where invasive species may be. For example, we compare different models and input layers, subsets of points, again, for training and test. We look at new data, and we may have different sizes of the area of interest. We may evaluate several different metrics. The area under the curve would be one, but sensitivity, specificity, the deviance explained, and maybe run Monte Carlo simulations to get a better idea of where that species is in space and time. We may use ensemble models, combining several models to get one result. We may screen input factors, predictor variables. If they're not that accurate, toss them out. Or if they're highly correlated, we'll only keep one of those variables in the model. And we'll always be skeptical of our results. We're going to treat results as a hypothesis rather than a result. These are visual maps, mapped hypotheses to be tested with better data later. And at the end, print really colorful maps because we all love them. How have they been used? And remember that 2007 map of potential habitat of the Asian carp a very preliminary model, we were worried about the size of this carp just going and swimming like crazy throughout the United States. In fact, when I look back just this week at a 2013 actual distribution map of Asian carp, we found that the model we made back in 2007 was very predictive. It was very accurate on where it might go. So the upper Missouri River was identified, areas around the Great Lakes had been identified, and even smaller areas in the eastern United States have been identified as potential habitat for the Asian carp. We use ensemble maps to help predict invasive species in Yellowstone National Park. We had several different models used to predict Dalmatian toadflax. We combine the results of the individual models, stack them on top of each other to give the managers a risk map based on several different models. So this was better than depending on any one model for an accurate result. We have distributional changes in downy brome or cheatgrass in Rocky Mountain National Park. If you had great data in 1996, you could predict where it was going to be in 1999. And if you had data from 1996 and 1999, you could predict where it was going to be in 2007. So these models have the ability to predict a species distribution in time. This is an example of an African fountain grass, the current distribution, and where it might be given climate change in 2040. This is a common request. Where is it going to be in the future? But that's just due to climate change. Really, this species is sold in Grand Rapids, Michigan, and a truck can carry it 500 kilometers a day, while climate change may change a species distribution 5 kilometers a year. Obviously, it won't take till 2040 to change the distribution of this species. We ship it around. So there are some urgent modeling and containment issues. One is the alien species on islands. In Hawaii, for example, 20 species per year may arrive on the island, and that's where extinction risk is very high. We may want to concentrate some of our modeling efforts on islands. We also want to be very concerned with apex predators like the Burmese python, brown tree snakes, Asian carp. Those kinds of high impact species must be examined first. Native fisheries have me worried. They're collapsing and we're losing species and subspecies due to alien fishes. I'm also worried about pathogens and zoonotic diseases that may spiral in numbers and extent and impact many plants and animals and even humans. We also have to require the very best remote sensing, monitoring, and modeling to keep up with these very many invasions. World trade is increasing 40-fold in the past 50 years. The invasion is just beginning. So the take-home messages from this episode: the world is one continent again with global trade. Invaders cost us a lot of money and they do harm, so we've got to stop them from entering. Invaders are the most urgent threat, in my eyes, to conservation. Humans contribute to the problem, but we can also contribute to the solution by finding the leading edges of these invaders and containing them. We're going to require the help of the NGOSs, the next generation of scientists that have to be a lot smarter and a lot faster than we are. So become a scientist. Get out there and save the world. Thanks for joining us on this episode of Nature's CSI, Creepy Stories of Invasion. If you have an idea for a show, send me an email. Check out our websites. And in the meantime, save the world. Thanks.